polymer particles occurs in a batch process. Okay? So the situation will be the following. We will introduce to a reactor the monomer, the water, and the surfactant, the emulsifier. Okay? We will use agitation to create a dispersion. Okay? Under this situation, we will heat the reactor until the desired temperature of reaction, and we will add an initiator. The situation that we have in this reactor, it will be something like this. You will have, here you have the element of the different ingredients that we have in the reactor. What we will have are monomer droplets, okay, in the micron size range. We will have, if the surfactant concentration that we use is above the critical micellar concentration, we will have micelles, which in the interior will have monomers. So the micelles will be swollen with monomers, okay? We will have also initiator or radicals, sulfate radicals. If we use a water-soluble initiator, we will have initiator radicals. The monomer, and this is something that I haven't mentioned so far, the monomer in emulsion polymerization is the oil phase. Okay? The monomer should be sparingly soluble in water. It needs to have a certain solubility in water. Okay? So this means that we will have monomer solubilized also in water, but the main monomer will be as big droplets. Okay? And some monomer will be also in the micelles. Okay, under this situation, so you have that the monomer will be distributed in droplets, aqueous phase, and the micelles. The emulsifier will be distributed in the stabilized in the droplets. Okay, all the surfaces will be covered by surfactant. So surfactant molecules will be in the droplets, plenty in the micelles. Some surfactant will be also in the aqueous phase, and some surfactant will be in other surfaces in the reactor, in the air-film interface, and attached also to the walls of the reactor. So, under these circumstances, now, what happens? The radicals that we generate thermally, the composed by temperature, these radicals will find, these radicals are water soluble, they are in the water phase. So they will find the monomer in the aqueous phase, because the radicals will not enter into hydrophobic surfaces, because they are very hydrophilic. So they are water soluble. So these radicals will find monomer in the aqueous phase and will react with the monomer in the aqueous phase. So we will start forming what we call oligoradicals. So radicals which are more hydrophobic than the original initiator radical. So these radicals which are more hydrophobic by adding monomer, now they are more hydrophobic, and at a certain point they will be surface active. They become like surfactants. This is hydrophilic, and this is getting more hydrophobic. So this now can absorb onto micelles or droplets. Okay? So if they absorb, they are much more micelles than droplets. Because of the size, micelles are in this range, 5 to 10 nanometers. Droplets are 1 to 10 microns. So the difference in size is tremendous. Okay? So we have plenty of more micelles than droplets. So the probability that these growing radicals find the micelles is much higher than finding monomer droplets. So therefore, they enter into the micelle. When a radical enters to a micelle, it finds plenty of monomer, and polymerization starts in the micelle, and this micelle in which a radical has entered becomes what we will call a polymer particle. Okay? So this is a way in which polymer particles are formed in emulsion polymerization, by entry of oligoradicals into micelles. if there are no micelles, if you were working with surfactant below the critical micellar concentration, there are another way in which polymer particles can be formed. In this case, this will not find micelles, therefore will continue growing, and it will continue growing until this becomes insoluble and precipitates. It precipitates, it will absorb surfactant, and then monomer will go to this and form a new part. So this mechanism, by formation of polymer particles by entry of radicals in the micelles, is called micellar nucleation or heterogeneous nucleation, and this way is called homogeneous nucleation. Okay? So these are two mechanisms that I will also cover tomorrow. Okay. Once the polymer particles are formed, polymerization reactions occurs in the polymer particles. So the monomer is consumed in the polymer particles. So since the polymer is consumed in the polymer particles, the monomer is transported from the big droplets to the polymer particles. There is a transfer of monomer from the droplets to the aqueous phase and to the polymer particles. So this is why it is very important that the monomer has certain solubility in aqueous phase. If you have a monomer which is very hydrophobic, it cannot be transported through the aqueous phase, so that you cannot polymerize in emulsion polymerization very hydrophobic monomers. Okay? So this is a limitation of emulsion polymerization for very hydrophobic monomers, because mass transfer of the monomer through the aqueous phase is not possible. Okay? So if monomer is transported where the particles, where polymerization is occurring, polymer particles are growing, and surfactant is needed because the particles are growing. The particles are growing because monomer is growing, polymerizing, particles grow. We need more area, we have more area, we need more surfactant to stabilize this, and the surfactant is transported from the micelles to the particles too. Okay? So we will continue doing this, polymerization occurring here. Micelles will be destroyed also because surfactant will go here from the micelles, or because the micelles are becoming polymer particles because of entry of radicals. So micelles will continue disappearing because two facts. Because we need surfactant to stabilize the growing particles, and because radicals will enter and they will become polymer particles. Okay? So this process continues until we run out of micelles. And we will end up in this situation. Monomer droplets shrink because we have less. The monomer has been transported to the polymer particles. Okay? And now we don't have micelles. Up to here is what is called the first interval of emulsion polymerization, where the polymer particles are formed. And now we enter in the second interval. In the second interval, we have now monomer in droplets, aqueous phase, and particles, no micelles. And the same for the surfactant. We don't have micelles. The surfactant is not anymore in micelles. So the polymerization continues here. Radicals enter into the polymer particles. We don't have micelles. Monomer is transported to the polymer particles. So the polymer particles grow, the droplets shrink. So and the process will continue in this second interval until we run out of monomer droplets. So droplets disappear, and we have particles which are growing. Okay? And we will enter in the third interval, in which we will have polymer particles swollen by monomer, and in this interval the monomer is consumed in the polymer particles. There will be always an equilibrium with some monomer in the aqueous phase, but polymerization will continue until completion in this interval. Okay? So one thing that is important to, for instance, to distinguish emulsion polymerization from suspension polymerization is that in suspension polymerization, the particles are formed in the droplets. Okay, so you have big droplets, but the initiator is oil soluble, so that you nucleate the droplets. In emulsion polymerization, you don't nucleate the big droplets, you nucleate in micelles. So the size of the particles is much smaller in emulsion polymerization than in suspension polymerization. In suspension polymerization, the size of the particles is micron size or even millimeters in some cases. Here we are dealing with nanometer scale polymer particles. Okay, a summary of the three intervals with some characteristics. Okay, the first interval, remember, is where polymer particles are formed. Okay? So, in the first interval, which occurs in very short amount of monomer consumed, here we have between 5 and 10% of the monomer is consumed depending on the type of surfactant and the type of monomer that we have. In this interval, in the first interval, the number of particles increases in red. So we are forming polymer particles. So number of particles increase. And the polymerization rate also increase. Right? The polymerization rate, which will be the slope of the conversion curve. So this is the conversion of monomer, how the monomer is consumed. This will be 100% conversion. So initially you see that very little conversion is needed to produce the particles. Okay? So in this first interval, number of particles increase, conversion also increases, polymerization rate increases because we have more particles, more polymerization. So the rate at which the monomer is consumed is faster. At the end of the first interval, we don't have any more micelles, so no more nucleation. And in this interval, we have droplets. And the droplets are transported to the particles. Depending on the monomer and the polymer and how much a monomer swells its polymer, the droplets might last longer or shorter. For instance, in terms of conversion, for vinyl acetate, at 20% conversion of vinyl acetate, there are no droplets. For styrene, we need 40% conversion to eliminate the droplets. In this interval, the number of particles remains constant, no more new particles generated, and the polymerization rate also remains more or less constant. So the slope here is 1 in the whole interval. Okay? So because the monomer particles are the particles are saturated in monomer, so the monomer concentration is mostly constant in the polymer particle. And since the number of particles is constant, the polymerization rate is more or less constant. So in this interval, number of particles is constant, monomer concentration is constant because we are at the saturation, we have droplets, and polymerization rate is also constant. Once the droplets disappear, monomer concentration decreases. So we consume the monomer that remains in the polymer particles, we are consuming this, number of particles doesn't change, and polymerization rate decreases because the slope of the conversion is decreasing as monomer concentration decreases. Okay? So this is a summary of the three intervals of the physical description of the emulsion polymerization. This is an ideal description. Okay? There are always, in reality, exceptions. Okay? So, but this is a good guide to understand how the polymer particles are produced and how the monomer and the polymerization rate proceeds in emulsion polymerization. Okay? So, there are exceptions. I will not talk about the exceptions, but you will find if you do research in emulsion polymerization. Okay? Polymer particles can be formed in the second and the third interval under some circumstances. If you run in a semi-batch, not in a batch process, there are other features that are important, but I think that for the fundamental understanding, this is enough. Okay, and now I will finish this second part with this concept, which makes, as I said before, a special emulsion polymerization, and it's the radical compartmentalization. Okay, so now you will understand qualitatively why I mentioned before that emulsion polymerization is unique, in which you can produce high molecular weights at high polymerization rates. And this is unique. There is no other polymerization technique by which you can obtain this. Let me see how much. I will try to use concept of homogeneous polymerization. Okay? I hope that you will understand. The polymerization rate in a homogeneous system, in a bulk solution, or even in suspension, is defined like the propagation rate, Kp, monomer concentration, and radical concentration, that I will call, to maintain the nomenclature that I have in the slides, like this. So, Kp is a function of the temperature, by the radius dependence, okay? And the molar masses, if I use, for instance, the degree of polymerization to define the molar masses, can be calculated like the polymerization rate divided by the termination rates. If you wish, summation of all the termination rates. Okay? So this is Kp monomer concentration, and if I consider only the molecular termination, this is okay. So now imagine that you want to produce high polymerization rates. Okay, you also need to know how the radical concentration can be calculated. If we assume the pseudo state, the quasi-pseudo state, the radical concentration in a homogeneous system is given by okay? So in any homogeneous system, if you want to increase the polymerization rate, you have two options. If you want to polymerize fast your monomer, two options. Increase temperature, because it will increase the Kp, or you can increase radical concentration, for which you can increase the initiator concentration. Okay? Now, what happens to the degree of polymerization if I increase the initiator concentration? If I increase the initiator concentration to increase the radical concentration, I increase this decrease. So if I increase this decrease. If I want to increase this, I have to reduce the radical concentration, therefore the polymerization rate will decrease. So there is no way in homogeneous systems to increase simultaneously the two at the same time. If you increase one, you decrease the other one. In emulsion polymerization, yes. Not always, but in certain conditions in emulsion polymerization, this is possible. Okay? And this is possible because radical compartmentalization. This is the concept that you have to understand for emulsion polymerization to understand why this is unique with respect to homogeneous systems. What is the radical compartmentalization? So radical compartmentalization means that in emulsion polymerization, the radicals are not in a homogeneous system. The radicals are distributed in the different particles. Of course, we have radicals in the aqueous phase, but the radicals enter into the polymer particles, and therefore then polymerization occurs here. There is very little polymerization in the aqueous phase in emulsion polymerization, a little bit, to create the oligoradicals that enter into the particles, but the main polymer is formed in the polymer particles. So, since the radicals are distributed, a radical in this particle doesn't see a radical in the other particle. This means that a radical here cannot terminate with a radical here. Whereas in solution polymerization, or even in suspension polymerization that we have very large particles, the radicals see each other and they can terminate between them. So this means that because we have the radicals compartmentalized in particles, the termination rate of the radicals is significantly reduced in emulsion polymerization. And since the termination is reduced, a radical will grow inside of the polymer particles until another radical enters. The particles are so small that it's very difficult to have two radicals growing at the same time in the polymer particle. Okay? So when a radical is growing and another radical enters, there is almost instantaneous termination. So that the radical will grow until it is alone in the particles. So what will control the molar masses here is the entry rate of the radicals, more or less. Okay? So this means that the overall life of a radical will be longer than the life of the radical in a homogeneous system. And it will grow more, so that the molecular weights will be higher. So we will have overall higher radical concentration, higher RT, but also longer life of living of the radical, higher molar masses. So and this is a feature of specific and unique of emulsion polymerization. Okay? This makes that, as I said, that the number of radicals that we will have in the particles will be really small, normally. Ideally, in the ideal case, we will have maximum one radical. We will have particles with one radical and particles with no radical. That will be switching. A radical will enter, we will have one radical. If a radical enters where a particle has a radical, it will terminate, we will have 0. So 1, 0, 1, 0, overall 0.5. This will be the ideal scenario where this is perfect. Okay? So not all the emulsion polymerizations are in this ideal scenario, right? But it is possible to be in this scenario. So let's see now the implications, now in a more quantitative way, of what I have discussed now. So let's imagine that we have a latex with 50% solids. So this means that 50% of the latex is polymer and the rest is water. Okay? But now we will consider two different particle sizes. In one, we will consider larger particles, and in the other one, smaller ones. In which one I will have more particles?
Second.
Here. Okay? So for the same solids, if I maintain the same solid, if I decrease the size, the number of particles will be higher in the radical. Okay? So now, let's assume that I have this situation, and that now I introduce an initiator, I hit, and I start creating radicals in this system. And that the rate of creation of radicals is given by this rate. And this rate comes from this equation. Okay, if you assume normal constants from the KD and for the concentration of initiator, and you multiply by Avogadro's number to have radicals per liter of latex per second, you get more or less this value. Assuming that this is 0.6, I think that I use this rate for KD, and I think that I use more liter for the initiator concentration, which are normal concentration. So this means that if I generate radicals at this rate in the two systems equally, now I can calculate which is the frequency of entry of the radicals per particle. Okay? So first, I have a calculation for the first class. So I assume that these are particles of 150 nanometers. I calculated the number of particles. This is the exercise I told you to do. I mean, have to calculate for these solids and this size, which is the number of particles. And the number of particles is 2.8 to the power of 17 in the first case. 2.8 particles per liter when the particle size is 150 nanometers. So the frequency of radical entry, which will be the rate of the radical generation, this Ri divided by the number of particles, this is the frequency that you have here. Okay? Or that means that one radical enters every 88 seconds to each particle as average. Okay? So that means that a radical will grow for 28 seconds in the polymer particle. Okay? Until another one will enter and they will terminate. Okay? If I do the calculation here, and I assume now that the particles are 80 nanometers, so 80 nanometers the number of particles now is 1 order of magnitude higher, almost 1.8 to the power of 18. The rate of entry now is 180 seconds. So every 180 seconds, a radical will enter because we have much more particles. So, and we have the same generation of radicals. So the rate at which the radicals enter is slow. So this means that in this scenario, the radical, if it doesn't suffer any other reaction, it will grow until another one enters. So where it will be the chain length larger? In this case or in this case? In the right. So a radical can grow longer, so I will obtain more or higher molar mass when I have more particles. And this is the consequence of the compartmentalization that we discussed. So this means that in emulsion polymerization, in addition to the temperature and the initiator concentration, I can control the molar masses by increasing the number of particles. Okay? So increasing the number of particles increases the molar masses. So you don't have particles in a homogeneous system, so you don't have the possibility to modify the number of particles, whereas in emulsion polymerization, yes. Okay? So this is one of the implications. The second one is the one that we mentioned before, is that because of this reduced termination, the radical concentration is overall is much higher in emulsion polymerization than in a homogeneous system. For instance, let us assume the same solid content of a latex, this size, this is the number of particles in this case, and we are taking these assumptions, which are assumptions because it doesn't hold for all the emulsion polymerization cases, and is that the radicals are formed in the aqueous phase, and they enter into the polymer particles from the aqueous phase. Okay? They are not lost in termination reactions in the aqueous phase that can happen. We assume that all the radicals enter. And we assume that also we have instantaneous termination, which is not always the case. So that if there is a radical, if another one enters, they will immediately terminate. Okay? This is again an assumption. We are dealing with ideal case. So under these conditions, is what I said before. Half of the particles will contain one radical, the other half will contain 0 radicals. Okay? So what is the concentration of radicals? The average number of radicals will be 0.5. If I multiply 0.5 by the total number of radicals, sorry, the total number of particles, I will have how many radicals do I have. If I divide this by Avogadro's number, I will have the mole, and in the particles per liter, I will have the concentration of radicals given by this equation. So this means that the total radical concentration I have in the reactor is also proportional to the number of particles. So if I increase the number of particles, I can increase the total concentration of radicals. And as I showed just in the previous slide, I can also increase the molar masses. So I can increase both the overall radical concentration, I can go faster in the polymerization, and I can increase the molar masses. Okay? The two facts. If you compare this with a homogeneous system, in a homogeneous, changing NP I can increase. In a homogeneous system, the radical concentration is given by the equation I put you before. So here, this is always constant. For the normal values that we use, for the composition of initiator, like the one I put you before, and for the same initiator concentration, the radical concentration you obtain is 4.5 to the power of minus 8 mole. In emulsion polymerization, in this case, you have 1 order of magnitude more, the concentration. And I can go even higher if I change the number of particles at the same temperature and initiator concentration that here. So that in emulsion polymerization, I can control the polymerization rate and the molar masses by controlling the number of particles that I generate. So I have to now have a tool to control the number of particles. So we will see this tomorrow. But today, to finish today, one more exercise here. We will calculate now how much time do I need to polymerize a certain number of polymer particles, okay? How much a batch of a process will do. And one way to do this calculation and compare with a homogeneous system is to calculate first how much time I need to create a chain. This is a concept that sometimes creates problems. How much time do you think that a chain takes to grow in a polymerization? Doesn't matter if it is emulsion or if it is a homogeneous system. Seconds. So this is a question that I always ask to my students. So if I have a reactor and I run a reaction in 3 hours to reach 100% completion, how much time do the chains need to grow until the final molar mass that they achieve?
Depends of temperature. Depends of temperature.
Depends on temperature, of course. At a given temperature, let's say 70 degrees, or any temperature that you want. I mean, the process of creating a chain is long or is short. I'm talking about chain growth polymerization, not step growth polymerization. Eh? In chain growth polymerization, how long does the growth of a chain take? Seconds, minutes, hours? In which range? Don't look at the sun. Seconds. Okay, too short. It can be less than a second. What happens is that you are, if the reaction takes 3 hours, you are producing chains, the first second, the second, the third, but you are generating chains under different conditions. Okay, that's why you get a molecular weight distribution, because you are creating chains with different molar mass as the concentration of monomer and the concentration of initiator is changing. Okay, so the growth is quick. It's like this. Chains are created at this pace. Okay. Okay. So let's calculate the time that a polystyrene chain with 1 million molar mass requires. And this is the calculation that you have here. Okay. So the calculation of the molar mass, the time that we need is done. This equation comes from the degree of polymerization. The degree of polymerization multiplied by the molar mass of the repeating unit is mm. This is not correct. This should be mm. Okay, and this is polymerization rate divided by termination rate multiplied by the molar mass of the monomer. This, in this case, is styrene. We are using 100. I'm not sure 100 as the molar mass of the styrene, or I think it's 1.4, but not important. And here, now, what we have is the RT is KT n divided by RT, and 1 divided by RT is the frequency of termination. Okay? So 1 divided by the rate of termination is the time that the radical will grow at this polymerization rate. So that's why I substitute 1 divided by t by the time of growth. And the equation that you have there is Kp and the molar mass, and the time of growth. Okay? So if now I want to calculate how much time I need to produce a molar mass of 1 million, a chain with a molar mass of 1 million, if I know the Kp of styrene, I know the concentration of styrene, and I know the molar mass, I can calculate it. So this is the calculation that you have here, done in a polymer particle. Okay, so that's why we have monomer concentration in the polymer particles here. So it turns that to create a chain of polystyrene of 1 million, I need 5 seconds. Okay, so now the calculation that we do there is, okay, how much time do I need to create a polymer particle of polystyrene of 150 nanometers? So if this is 150 nanometers, how much time do I need to create a polymer particle? So what we do is we calculate how many chains of 1 million enter here. Okay? So we are calculating the time that we need to produce a polymer particle of 150 nanometers with all the chains of 1 million. Okay? If you calculate the volume of the particle from the volume, the mass, if you divide by the mass of each chain, then taking into account Avogadro's number, you can calculate how many chains of 1 million enter in a particle of 150 nanometers. Okay? It's just a geometric calculation. The volume of a particle is spherical particle, 4 divided by 3p, the radius to the power of 3, density of the polymer, and this is the mass of all the chains. This is the number of chains, and this is the mass of a single chain. Okay? From this calculation, you get that in this particle, you can have, in 150 nanometers, you can have 1,000 chains of 1 million. Okay, if one chain requires 5 seconds, 1,000 chains requires 5,000 seconds, 1 hour and a half. If we assume that we can create the particles with the mechanism I told you, basically at the same time, most of them are the same. Remember that all the particles are generated in very little conversion. Okay, so that mostly all the particles start growing at the same time. So I can grow all the particles at the same time. I will need to create a latex of polystyrene 1.5 hours. Have someone of you run a polymerization of styrene in homogeneous in bulk or in solution? How much time do you need to create a solution of polystyrene in bulk or in homogeneous? More than 10 hours minimum. More than 10 hours. And probably you don't reach 100% conversion. In emulsion polymerization, in 1.5, your reaction is finished. So you have converted. But emulsion polymerization, because of the radical compartmentalization and the higher radical concentration, because we have much less termination. And this is the reason. But that you avoid termination of the radicals because you have the radicals in separated particles. You run at this speed. And this with particles of 150 nanometers. If you have smaller particles, you have more particles, you need less chains in the particle, and you finish in less time. Okay? So you will go faster, and you will produce, as we said, higher molar masses by just changing the number of particles in the process. And to change the number of particles, which is the variable that you have? From what we have discussed in the description, how can you control the number of particles? Surfactant. So if you change the surfactant, you change the number of micelles that you create. So the higher the surfactant concentration, the higher the number of micelles, the higher the number of particles. So you can control without touching temperature on the initiator. You can change the number of particles so that you will obtain more particles faster and higher molar masses. And with this, we can stop here. If you have doubts, we still have some minutes. Anything that you want to ask me or any doubt that you have, we can discuss today or tomorrow at the beginning of the class. If you wish, I can ask you again. If you can go through your notes, and if you have any doubt, you can ask me. I will send you I will send Claudia the slides, and she will send you the slides. Yes?
You can use these emulsion particles to produce nanocarbon particles too.
Which nanoparticles?
Nanocarbon.
What do you mean by nanocarbon?
You can use to put together them two and form another big package and another with the nanocarbons you're using.
Do you mean carbon nanotubes or something like that?
Like that? I don't know.
No, it's not easy to do this, because I mean, you can form crystals when you make, because remember that these particles are dispersed in water. So if you want to make aggregates, you have to evaporate the water. Okay? If you do this evaporation slowly, you can organize, you can create arrays of particles, and you can create, and the TG of the polymer is high, you can create crystals. You can create, depending on the polymer, you can create these organizations of particles. Yeah, in arrays. Not nanocarbon tubes, but you can have some kinds of organization. I mean, these kind of nanocrystals are used to polarize light and things like that. I mean, there are some applications which are not the main applications of these lattices, but this is something that is possible to do. I mean, to create crystals by organization of the polymer particles during evaporation. Yeah. So you can create templates also with these polymer particles.
If I use a combination of monomers, how I calculate this?
The same.
Same?
Nothing changes. I mean, imagine that you have two monomers, no? You have a copolymerization, which is normal. In emission polymerization, this will be the average, so that the average, if you have a copolymerization, will be, imagine, let's take that you have two monomers, so it will be Kp 1,1, monomer 1, Kp 1,2, monomer 2, plus Kp21, monomer 1, plus Kp22, monomer 2. So, and you can extrapolate to any number of monomers. But this is the same in homogeneous systems.